In this final segment on analyzing two-group data, we want to take a look at how we can quantify the differences between the groups at the post-test. This is the most meaningful measure here. These other measures are somewhat meaningful, but this one is the most. This one tells us whether or not our intervention actually made a difference compared to a control condition. And we do that using a statistical test called an independent samples t-test, and then out of the independent samples t-test, we compute something called an effect size. So let's take a look and see how we do that. It's pretty straightforward. Probably brings back some bad memories about statistical stuff, but hopefully not. I'm hoping that by the time you're done with this, you'll see some value in understanding at least a handful of statistical tests. So one of the things that we have to do as a preliminary, and I think this is going to be mainly for Mac users. It could apply also to Windows users. I need to check on that, but I know it applies for Mac users. So one of the things that we have to do is add something to our Excel installation. Essentially, it's called a data analysis pack. I believe that's what they call it now, or the analysis pack. So let me show you how to do that. Basically, hopefully you have a menu bar. There are two in the Mac environment. We actually end up with two. For some reason, two menu bars. So we're going to go to the top menu bar, and we want to click on Tools. And we want to go down then to Excel add-ins. And you might have to do this in Windows, so you can kind of follow along. So click on Excel add-ins. And you'll see you have a couple of add-ins. I have two, and I think you'll probably only end up with two. So what you do essentially is put a check mark in the analysis tool pack, and then click on OK, and that should install it basically, and it will give us access to a handful of statistical tests that we need to do our work. So what we want to do when you I don't know if you remember this or not, but when you have two groups and you have a continuous outcome variable, you use something called an independent samples t-test. And it's important that outcome is continuous. If it was a binary, if it was like a yes/no, or presence and absence of something, we would use a different kind of statistical test. In this case, these are continuous scores, or they're measured at the continuous level of data. So I hope that all made sense, and hopefully you've read some stuff so you'll remember at least some of the terms. So what we need to do is go into our data tab. And we're going to go, before we get too far along, let's go to our data. We're in our data tab. So what we want to do is come up with this independent samples t-test. And so I want to show you how to get from here to here. This is kind of how we've done this in the past. So from here, we go into data analysis. And you can, if you kind of scroll through this, you can see the various fairly limited statistical tests available to us. So what you're going to see, we're going to use two types. We're going to use the paired two sample tests for our next example, but for now we're going to use the two sample t-test, assuming equal variances. And this is sort of a complicated kind of topic in some ways. There's actually a test that you can give to see if the variances of of two distributions are not equal. But we're going to use the standard deviation as a proxy. I don't know if you remember, I talked about maybe using these standard deviations as a proxy for this. So if your standard deviation values are fairly close, and these are fairly close in the scheme of things, and what you want to do is use the two sample assuming equal variances test. You almost always want to use this, even if there's some variation. It's a confusing topic for people, but given what we're after, you can be pretty safe in using the equal variances test. I hope any of that made sense. So anyway, click on OK. And this will take us into a dialog that looks like this. So what we want to do is we'll put in for our input values, we're going to put in our post-test scores for our program group. And then you can hit enter. And then we'll put in our post-test scores for our control group. Let's see if we can get it to go down there and then hit enter or return. We'll leave alpha at 0.05. We won't put any hypothesized mean difference in there. That usually requires information that's a little more fancy than what we have, or a little bit more advanced than what we have. So we're just going to go with the defaults for this, and we're going to have it put it in a new worksheet. I don't know exactly what ply means, but I know it's going to go into a new worksheet, and you can see what happens. It will be added down here. And click OK. So it doesn't give us a title. Actually, I gave it this title, so you get a title. You just get a new sheet, and you can see that we have our output from this. So usually what I do is just go in and click and highlight, and control click or right click and do format cells, and put in a number. And I might put in 3 for, no, let's just do 2. That's not a big deal. So let's just do 2. So let's see what we have here. We've got our mean of 81. We know that's true. 63 point. Ooh, that one didn't format. Let's just do a real quick format on that. I'm not being too crazy about this, but let's it makes it a little easier to look at. So, and our variances, which are not terribly off in our observations, 32 and 28. Some of these things you don't have to really know all that much about, but what you do need to know about is this p-value. And we'll do a two-tailed test, basically. So this is a p-value, probability value. And in order to determine if a difference is statistically significant, hopefully some of these terms will be familiar with to you. We're looking for a value of less than 0.05 for a finding to be statistically significant. So you can see here that our mean difference between the two groups on our outcome measure is statistically significant. That is, this value is actually less than the 0.05 threshold. So that's a good thing, and in the old days we would have been very happy with that difference. But in the new days, we want to know a little bit more about it. So I'm going to go over to, I'm going to show you how this gets done, and you will have this. So, and I've had students who actually caught right on to this and are really quite good at it. So let's go over and let's go over to the independent samples t-test and take a look at that. This is the one that I ran essentially. So it's the one that we have available to us. So we know we're statistically significant because of our two-tail test, our p-value for our two-tail test. But what we're really interested in is the effect size. As you know, and as I've said at least 12 times, it's the effect size that we want to know about. And in this case, we're going to compute something called a Cohen's d. Now, hopefully you've read through some of the material we've provided for you on statistics and especially effect sizes. So you should know something about this. So I'm not going to get into a long discussion about it other than to say Cohen's d is a very popular standardized mean difference that you will not only run into if you're going to do this kind of evaluation yourself, but certainly in forest plots and reading the literature. So there are a couple ways to compute Cohen's d, but this is the easiest way if you have data from a statistical test like this output. So you can see that in this, and don't get freaked, this is just very straightforward, that Cohen's d is equal to the t-value that we have here, 4.218, times the square root of our n1 plus n2, which is 32 plus 28, divided by n1 times n2, which is 32 times 28. So if you did this math, if you worked from here and did this and did this and did the division and then did the square root and then did the multiplication, you would end up with a t-value of 1.09. So the other way to do it is to actually do it in Excel. I'm just going to show you this real quickly. It's actually kind of cool, and honestly, if you catch on to this, you're really going to be kind of a solid user of Excel, at least for this kind of thing. So what we're going to do is actually use the output from our t-test, and we're going to compute a Cohen's d using that value, using a formula that we develop in Excel. Now, this is not a function. This is really a formula, and you can see if you look through this, and the parentheses are a little bit confusing, but they sort of set the terms into where they need to be to do the computation. So you can see, so just take a look at this, don't have a conniption. So we have our t-value is 4.218 times, so we have the times here, the square root of, and then we've got our 32 plus 28 in a numerator here, and we put a parentheses around that, and then we have that divided by 32 times 28, and we have those two terms in parentheses, and then we have the whole division thing of those products in sums in parentheses, and then then Excel takes the square root of that. Hopefully you'll remember the my dear Aunt Sally, multiplication, division, addition, subtraction rule, and using parentheses. Maybe if you had some algebra, you know how to use parentheses. So hopefully this makes sense. It's actually, and if you end up with some weird value, if you replicate this, it's probably because you didn't get the parentheses in quite the right place. And I'm not going to lie to you, I have trouble with that sometimes. So there you are. So now we have an effect size, Cohen's d, a very helpful effect size, because it actually gives us a sort of magnitude that the statistical significance didn't. And this is what we know, that a Cohen's d of 0.2 is a small effect, of 0.5 is a medium effect, of 0.8 is a large effect, and a 1.0 or above is considered to be a very large effect. So what we have here is a statistically significant finding, and what we call with our Cohen's d a practically significant finding. So, and that's very helpful, and this is what would get reported if you were actually ever going to write this up, or if you read a study about this 1.09 would be the effect size that you would see, and people would be very happy with that, essentially. I hope that all made sense. This all assumes that you've done some reading about effect size that we've provided for you. This is sort of how you get them, but how you think about them and interpret them is in some of the readings that we've given you. So we do that. So you have to compute a t-test in order to do this computation of d to use the output from the t-test. There are some other ways that you can do it, but those are totally for another day when you're in your PhD program and you're doing this stuff. So let's pop back over to our data and see how we embedded that. So we just really literally typed in our mean difference. We didn't put it in as a formula, mainly because it would have been complicated. We needed to be in the sheet where the data values were. Actually, we could put it in here, but we didn't. So that's the point. The other effect size that we're interested in is really literally the difference between the two means, the group means. And you can see that we've done the math here with a simple little formula. We just typed in our equal sign and we subtracted our control group mean of 63.43 from our control group, from our program group mean of 81, and you can see that it's a 17.57 points difference. Sometimes interpreting mean differences is difficult. There's no standard like the 0.2, 0.5, 0.8 cutoff for Cohen's d or other standardized means differences. So, but in this case, we would be very happy with 17 point, almost 18 point difference between the two groups on our outcome, knowing that it's a 0 to 100 scale. So that's a big chunk if you think about. 20% would be sort of 1/5 of the data in some ways. So, but you could actually drive yourself crazy thinking about it. But we would think that a 17.57 difference on that scale would actually make some sense. And just one last thing. So what we've really done here is answer the question. So on this chart, is this difference between these two groups at post-test a substantive difference? And we have included from our analysis that it is both statistically substantive and it's also practically substantive, with practical significance being indicated by Cohen's d. So that's analyzing two-group data. In this case, it's a randomized control trial. If we had two-group data that didn't do randomization, did some purposive selection and assignment, it would be a quasi-experimental design. But we would do the same analysis on a quasi-experimental design. We would just be a little more suspicious in some ways, or a little bit more questioning about thinking about the results in all, but it would be the very same process essentially. So that concludes our 3 presentations on analyzing two-group data. Hopefully, it will help you think about any program evaluations you might do as your projects where you've got actually an experimental or a program and a control group. You could use the spreadsheet as a shell. I've had students do that, plugging in their own data values and kind of replicating analyses. It actually works really pretty well to do that. So our last topic will be analyzing single group, simple pre-post data, which a lot of students end up doing. So that will be coming up next.